Hello everyone. In this video, I'll give you an introduction to discrete uniform distribution. To start discussion, let's have a die. When we roll a die, we'll get the following possible faces. These are the possible outcomes when we roll a die. Now, if rolling a die is fair, then all of these have equal chances to occur. Since there are 6 of these, we can divide the total probability 1 by 6. So each face has 1/6 chance to occur in each roll. Since each outcome has the same probability of occurrence, then they give rise to a discrete uniform distribution. Now let's discuss what is a discrete uniform distribution. In a discrete uniform distribution, each outcome is equally likely to occur. This is a classic definition, and this is what you see in most textbooks. I will update this later as we go on with the discussion in this video. And also, for the discrete uniform distribution, the number of its outcomes is finite since it is a discrete distribution. Let's have an example. I just have shown you the dice example. Since it's fair, then each of its possible outcomes has equal chance to occur. And since also the number of outcomes in here is finite, then it can give rise to a discrete uniform distribution. Another example is, let's say you are in a lottery game. You are playing a game with your friends. Let's say the prices are random and can be any of these, $30, $40, and so on. If choosing any of these prices are purely random, so that the chances of getting any of these are equally likely, and since the number of possible outcomes in here is finite, then this also can give rise to a discrete uniform distribution. Now, to formally define this distribution, I have to introduce to you its random variables. We designate its random variable by capital X. A random variable, even though it uses the term variable in here, is actually a function, and for discrete uniform distribution, it is a function that returns an integer given an outcome. For example, if we have an outcome, let's say a face of a die with 4 dots in it. If we apply a random variable in it, it should return an integer. For example, the random variable can return 7. It's just an example. To understand it, let's have a more complete example. Let's have the lottery game example again. The lottery game has these possible outcomes of $30 up to $70. And let's say they are all equally likely to occur. And we put here the values of its random variable. We can put here 1 to 5. You can put here any values as long as they are integers. So given a possible outcome, if you apply a random variable in it, x of s, this random variable, should return its corresponding integer. So for each outcome, there is a corresponding value of the random variable. Since the possible outcomes are real number, we can have an equation for this random variable. So from here, we can determine the values in here by just dividing the outcome, which is s in the equation, by $10, and then minus 2. So this random variable is a function, given an outcome s, which is any of the values in here, and it returns a value which is a value in here. Well, the values in here does not necessarily need to start from 1. This is a standard case anyway, where we start from 1. We will discuss the different cases in the next slide. In here, we can also start from 3. So we have changed the values of the random variable, and they are now from 3 to 7, instead of from 1 to 5. It's no longer a standard case. And we can also update the expression of the random variable. So from here, to get the values in here, we just need to divide the outcome by $10. And this equation is now simpler than before. And these values in here, when combined as a set, is referred to as the support of this distribution. And in symbols, we can represent it like this. support of the random variable x, where x is our representation of the random variable. Now for discrete uniform distribution, we have several cases. For each case, its mean and variance expressions are mostly different. So let's now discuss the different cases in discrete uniform distribution. We have here the different cases in discrete uniform distribution. We have the general case, the consecutive case, and the standard case. Let's start with the general case. In this case, the support is a set of integers. So the only restriction in here is that the values of the random variable are integers. This is actually how the discrete uniform distribution is basically defined. And for example, we can have values like these, where the values are just a set of integers. Then we have the consecutive case. And in this case, the values are consecutive. So if A is the lowest value in here, and B is the highest, then any integer in between A and B must also be in here. And we have an example in here. The lowest is 12, the highest is 17, and any integer in between 12 and 17 are also in here. So the integers between 12 and 17 are 13, 14, 15, 16, and they are all in here. But if in case this 14 is missing in here, then it is no longer a consecutive case. All of the integers in between 12 and 17 must be in here to be considered as a consecutive case. Then we have the standard case. And in this case, the values are increasing consecutively from 1 to n, where n is the number of values in this set. This is the most common in textbooks. This is actually a special case of consecutive case, where A is 1 and B is n. For example, we can have values like these for this case. The values are from 1 to 5. So it started from 1, then increasing consecutively until 5. And this 5 is actually the number of elements in here. So these are the different cases in discrete uniform distribution. And each of this case has mostly different mean and variance formula that will be introduced a little later in this video. But let's go back to the definition. So now since we have discussed the random variable for this distribution, we can now correct this description in here. Instead of each outcome, we have to change it to each value of the random variable. It is for the rigorous definition of the discrete uniform distribution so that we can apply our expressions correctly. So the equal probability in here actually refers to each value of its random variable instead of each outcome. So in the example, discrete uniform distribution requires that the probabilities of occurrence of each value in here are equal, even though the probabilities of occurrence in here may not be equal. This is contrary to our previous description for a discrete uniform distribution. But these outcomes can also have equal probabilities in a special case, like this, where there is a one-to-one relationship between the possible outcomes and the values in here. But if we don't have a one-to-one relationship, for example, let's say both these $30 and $40 are designated with 4 as their value of the random variable, instead of separate 3 and 4. We have these values now. We now have only 4 values instead of 5 compared to before. And then we can put their probabilities of occurrence in here. So as you can see, the probabilities of occurrence of the values in here, which are these, are all the same. They are all 0.25. Now the probabilities of occurrence of these 3 outcomes are the same with the probabilities of occurrence of their corresponding values of the random variable. So their probabilities of occurrence are each 0.25 as well. But for these two, their probabilities of occurrence must add up to 0.25. So we can have, for example, 0.1 for $30 and 0.15 for $40. And if you add these two, you'll get 0.25. So as you can see, the probabilities of occurrence of the outcomes in here, which are these, are not the same, even though the probabilities of occurrence of the values in here, which are these, are the same. So even though we have unequal probabilities of occurrence in the outcomes, we can still describe this distribution as a discrete uniform distribution, as long as the probabilities of occurrence of the values are the same, and of course, the number of outcomes is finite. So that's for the definition of the discrete uniform distribution, which is consistent with the expressions that will be shown later in this video. So now let's discuss the graph of the distribution. Let's draw the graph of the discrete uniform distribution. The discrete uniform distribution can have several values of its random variable. The values in the x-axis are the values of the random variable, and from the previous slide, they are integers. In the lottery game, for example, that we have discussed, we have the values 3, 4, 5, 6, 7. This is just an example. The values in the y-axis, on the other hand, are their corresponding probabilities to occur in the experiment. And being in uniform distribution, their probabilities of occurrence are the same. Let's designate their probabilities of occurrence as the variable p. So each value in here has the probability p to occur in the experiment. So this is the graph of the discrete uniform distribution. So if you see a distribution graph which contains discrete values and the graph is flat like this, then the distribution is likely a discrete uniform distribution. So now let's discuss the common expressions that characterize the discrete uniform distribution. Let's have the expressions in here. We have here the expressions that characterize the discrete uniform distribution. We have here the expressions for the support, for the probability mass function, or PMF, for the mean, for the variance, and for the moment generating function, or MGF. And we have them for different cases in discrete uniform distribution. Remember the definition of these cases. We have already discussed in here the descriptions of the different cases in the discrete uniform distribution. We have the general case, the consecutive case, and the standard case. Let's then discuss the different expressions for those cases. In here, I have provided the descriptions of the supports for the different cases of the discrete uniform distribution, which will serve as our guide for the cases in here for our discussion. For the general case, the values are any integers with size n, where n must be finite. For the consecutive case, the values must be consecutive. In the general case, the values may not be consecutive, but in consecutive, the values must be consecutive. For this consecutive case, it starts from A and ends with B, and the number of values in here given these parameters A and B can be computed using this formula. For the standard case, it is similar to the consecutive case. The values must also be consecutive, but must start from 1, instead of any integer a in here. Then, if you count the number of values in here, the last number in here will be equal to the number of values, which is n. So in this case, the b in the consecutive case is n in the standard case. For the probability mass function, or PMF, they all have the same expression, 1 over n. In the consecutive case, the n can be determined from the parameters a and b by using this formula as discussed. For the mean, we have these expressions. For the general case, the values can be irregular, so we have this expression. And because each x sub I has the same probability to occur, we can just take the average of them as its mean. This is the formula for averaging a set of numbers. For consecutive case, we have parameters a and b, which are the lowest and the highest values respectively. And the mean can be determined by just averaging these two. In here, the computation is much easier. We just need to average these two values, the lowest and the highest values. Unlike in here. In here, we have to average all of the values. So if we have, for example, 100 values, we have to get the average of 100 values. But in here, we just need to get the average of the two numbers. Now for the standard case. In standard case, the value starts from 1 and ends in n. So the a in the consecutive case is 1 in the standard case. And the b in consecutive case is n in the standard case. In the standard case, by knowing only the number of values, n, we can determine its mean. Then for the variance, in the general case, similar to the mean, we have to involve all of the values in the expression. The expectation of x in here is actually the mean, so we can substitute the formula for the mean in this part of the formula of the variance. And in here, there is some averaging that happens in here. The variance is actually the average squared distances of the values from their mean. For the consecutive case, we have this expression, and it is dependent only on n. If a and b are the only parameters given, instead of this n, then this n can be determined again using this expression in here as discussed. Then in standard case, the expression is the same with the consecutive case. Since standard case is similar to consecutive case, but a is 1 and b is n. And since the expression does not depend on a or b as long as n is the same, so as a result, the expression for the standard case is the same with the consecutive case. For the moment generating function, for the general case, similar to mean and variance, we have to involve all of the values in the expression. And there is some averaging that happens because of the constant probability of occurrence in the distribution. So the moment generating function in here is actually the average values of e raised to t times x sub I. Then, for the consecutive case, we have this expression which we will derive in one of the next videos. And in standard case, it's similar to the consecutive case, except that a in the consecutive case is equal to 1 in the standard case. So the a in the standard case is gone, and then the rest of the expressions are the same. So these are the common expressions that characterize the discrete uniform distribution, and we will discuss more about these expressions in later videos. Anyway, this is just an introduction to discrete uniform distribution, and there are many more videos to come for this distribution. I hope you enjoy watching this video. So good luck for the next video, and don't forget to subscribe in my channel.